everyone, welcome to our channel Knowledge of. Friends, subscribe to our channel and click the bell icon for the latest update. Today we're gonna start with chemistry class, and this is your class number 148 class. And as you know, we had completed your 147th class of the session till here. And first of all, here we had started with the equilibrium in the last unit of the session. Hopefully I will be ending up the equilibrium and the chemistry part in this session only. And first of all, that's a huge request कि अगर आप हमारे चैनल फर्स्ट टाइम देख रहे हो या अभी तक आपने हमारे चैनल को सब्सक्राइब नहीं किया है, ऐसा ह्यूज रिक्वेस्ट कि हमारे चैनल को सब्सक्राइब करो सो दैट हम जो भी वीडियोस डालें वो आपके पास सबसे पहले पहुँचे। एंड सेकेंडली, अगर आपको हमारा वीडियो अच्छा लगे तो प्लीज़ हमारी वीडियो को लाइक शेयर और सब्सक्राइब करो सो दैट ज़्यादा से ज़्यादा लोगों के पास वीडियो पहुँचे और ज़्यादा से ज़्यादा लोग इसका यूटिलाइजेशन भी कर सकें। Now in today's class we'll start discussing about the lowest acids and bases, because last class में हमने acids and bases से related किया था, उसके बाद हमने numerical भी किया था. And now we'll discuss about the Lewis acids and bases. In this, G.N. Lewis in 1923, G.N. Lewis in 1923 defined an acid as a species which accepts electron pair and the base which donate an electron pair. As far as the bases are concerned, there is not much difference between the Bronsted-Slurry and the Lewis concept, as the base provides a lone pair in both the cases. So however, in the Lewis concept, many acids do not have proton, and a typical example is the reactions of electron that is defined by BF3 with NH3 that we had done here. So here you can go on through with BF3 plus NH3 with having a lone pair that reacts and give BF3 that is of NH3 here. In regard of that, here we can say that BF3 does not have. So here we can say that with regard of that, BF3 does in here that is BF3 that BF3 does not have a proton, but still act as an acid and react with NH3 here, and by accepting its lone pair of an electron, the reaction can be represented as here it is represented an electron deficient species like AlCl2 with like I'm talking about AlCl2 plus carbon monoxide 3 plus, that is Mg2 plus, etc., that can act as Lewis acid, while the species like H2O, NH3, and next is your OH minus. These were which can donate a pair of electron that can act as Lewis bases as well. These were the Lewis bases and these were act as Lewis acids here. With regard of that, you have to understand what are the Lewis bases and Lewis acids in regard of it. Now we'll discuss about the question, that is the classify the following species into the Lewis acid and the Lewis base and show how would they act as such. In terms of HO minus, if I'm talking about, this is an hydroxyl ion is a Lewis base as it can donate an electron lone pair that is your OH minus. That I can write it down for you, that you can just write it on. Hydroxyl ion is a Lewis base as it can donate an electron lone pair, that is your lone pair here, it will mention, and that OH. This will be assigned here as in the case. Now for the second we have is F minus, that the fluoride ions act as a Lewis base as it can donate any one of its 4 electron lone pair. So you can just write it down. Fluoride ions act as a Lewis base as it can donate any one of its 4 electron lone pair. For the third one we have is your H plus here, as H plus is mentioned here is the proton as a Lewis acid as it can be accept a lone pair and of electron from the bases like hydroxyl ion and a fluoride ion. So you can just write it down. A proton is a Lewis acid, as it can accept a lone pair of electron from bases like hydroxyl ion and fluoride ion. Now talking about the BCl3 here. With BCl3, that is BCl3 act as Lewis acid, as it can be accept a lone pair of electron from the species like ammonia and amine molecules. So we can write it down. BCl3 act as a Lewis acid, as it can accept a lone pair of electrons from species like ammonia or amine molecules. Now we'll talk about the next heading that we have here is your ionizations of acids and bases. In regard of the ionizations of acids and bases here, and Arrhenius concepts of acids and the bases becomes useful in the case of the ionization of acids and bases, as mostly the ionization in the chemical and the biological system occurs in the aqueous medium, and strong acids like that is percolic acid, or which we can say that the percolic acid has been written like HCl O4. This is a percolic acid, and hydrochloric acid you also know that is HCl here. And with regard of that, the hydrochromic acid, that is your HBr, and the that is hydroiodic acid, that is HI, nitric acid, that is HNO3, and the sulfuric acid, that is H2SO4, are termed as here in the terms of, because they are almost completely dissociated into their constituent ions and is an aqueous medium, therefore acting as a proton, that is H plus donors. Similarly, the strong bases like lithium hydroxide, that is LiOH, and sodium hydroxide, that is NaOH, that potassium hydroxide, that is KOH, cesium hydroxide, that is CSOH, and the barium hydroxide, that is BaHOH whole twice, and are almost completely dissociated into the ions in the aqueous medium, giving the hydroxyl ions OH minus. And according to the Arrhenius concept, they are strong acids and the bases, and they are able to completely dissociate and produce the H3 plus or H3O plus or OH minus ions respectively in the medium. So alternately, the strength of an acid or a base may also be gauged in terms of the Bronsted-Lowry concepts of acids and bases, and wherein a strong acid means that a good proton donor, and a strong base implies a good proton acceptor. Strong base implies a good that is a proton acceptor, that consider the implies of a good proton acceptor, like acid base dissociation equilibrium of a weak acid that we have is Ha. This is an HA, that is in aqueous state, and plus H2O, that is in the form of the liquid state. Here this is H3O plus, that is in aqueous state, and A minus, that is in aqueous state as well. In the reference to the HA, this is your acid, this is base, this is your conjugate acid, and this is your conjugate base. Here with reference to this, in this we saw that the acids or the bases dissociation equilibrium is dynamic, involving a transfer of proton in the forward or the reverse direction. Now the question arises that if the equilibrium is dynamic, then with the passage of the time, which direction is upward? So yeah, what is the driving of forces behind it? In order to answer all these questions, we shall deal into the issues of the comparing the strength of that two acids or bases, and involving the dissociation equilibrium as well, and consider the two acids like HA and H3O plus, that is present in the above mentioned acid dissociation equilibrium. We have to see which amongst them is the stronger proton donor, and which ever that whichever exceeds in its tendency to of donating a proton and over the other shall be termed as the stronger acid, and the equilibrium will shift in the directions of weaker acid, and say that like if Ha is a stronger acid than H3O plus, and then of course Ha will donate the protons and not H3O plus here, and the solution will mainly contain A minus and H3O plus ions, and that the equilibrium moves to the directions of the formation of weaker acids and the weaker base as well. In regard of that, we can say here, so here because the stronger acid donates a proton to take the stronger bases as well, and here it follows that a strong acid dissociate completely in water and the resulting base formed would be very weak, that is the strong acid have a very weak conjugate base. Strong acids like the percolic acid, as I told you about the SeLO here, and that is that the hydrochloric acid, that is HCl, hydrochromic acid, hydrobromic acid, that is your of course HBr, and then that is hydroiodic acid, that is HI, and the nitric acid, that is HNO3, and the sulfuric acid, that is H2SO4 with a give conjugate bases ion, that is ClO4 minus and Cl Br2 Br, and that is of I minus, and of course NO3 minus and HSO4 minus as well, which are much weaker bases than the H2O. Similarly, a very strong base would give a very weak conjugate acid. On the other hand, a weak acid say like Ha is only the partially dissociated in the aqueous medium, and thus the solution mainly contains the undissociated Ha molecules. And typically weak acids are nitrous acid, that is HNO3, in a hydrofluoric acid like HF, and the acetic acid, that is CH3COOH. It should be noted that the weak acid have a very strong conjugate bases, and for example like NH3 O2 minus and H minus are very good proton acceptor, and thus much stronger bases than the H2 as well. In regard of that, certain water soluble organic compounds like that is phenolphthalein, and that is bromothianol, that blue behave as a weak acid and exhibits a difficult. So which exhibit different colors in their acid, that is of HLN, and the conjugate base Ln a minus form. So here we have an equation that HIN, that is an aqueous state here, and that is the plus, this is an aqueous state, plus H2O, that is in the form of liquid state, and give H3O plus aqueous state, and Ln, that is IN, that is in aqueous state. In regard of that, here this is your acid indicator, and where this is your conjugate acid, and this is your conjugate base, yeah. With regard of that, such a compound are useful as indicator in acid base titration and finding out H plus ions concentration here. Now we'll talk about the another one, that is the ionization constant of water and its ionic product. In this, that some substance like water are unique in their ability of acting both an acid and a base. We have seen that in the case of the water, as well as that the presence of an acid, that is Ha, it accepts a proton and acts as a base, while in the pressure or that is a pressure of a base, presence of a base and of B minus, that it acts as an acid by denoting a proton in pure water, and on H2O, and another water molecule accepts a proton and acts as a base of the same time. The following equilibrium exists here, we have an equation, that is H2O, that is in the form of the liquid here, plus H2O liquid here as well, and with regard of that, that gives you that H3O plus aqueous and plus OH minus aqueous. This is the vice versa, the reverse reaction, H3O plus aqueous plus that is OH minus aqueous gives H2O liquid and H2O liquid as well. In regard of that, it is acid, this is base, this is your conjugate acid, and this is your conjugate base. With regard of that, the dissociation constant is represented as K equals to H3O plus, OH and then upon H2O, where the concentration of water is omitted from the denominator as the water is a pure liquid and its concentration remains constant, where H2O is incorporated within the equilibrium and constant to give a new constant, that is the Kw, which is called as ionic product of water. This is the Kw, which is known as ionic product of water. So here that Kw is equals to H plus of OH minus. This concentration of H plus has been found out experimentally is your, that is 1.0 into 10 to the power minus 7 m at a 298 temperature, and as dissociations of water produces equal number of H plus and OH minus, the concentration of the hydroxyl ion, that is OH minus, and equals to H plus, and that is equals to 1.0 into 10 to the power minus 7 m, and thus the value of the Kw is at 298 Kelvin. Now the Kw is equals to H3O plus and OH minus equals to 1 into 10 to the power minus 7 whole twice, that gives 1 into 10 to the power minus 14 m square here as well. The value of the Kw here is temperature dependent, as it is an equilibrium constant. The density of the pure water is 1000 gram per liter and its molar masses is 18.0 gram per mole. And from this molarity of the pure water can be given as like H2O. If I'm finding out for the H2O, H2O is equals to 100, that is 1000 gram per liter, 1 mole upon 18.0 gram per mole. From this, the molarity of the pure water can be given as like H2O, that's what we had find it out, and that is equals to 55.55 mole here. With regard of this, therefore the ratio is dissociation of the water to understand that is undissociated water, that can be written as like 10 to the power minus 7 of 55.55 as well, and that is equals to 1.8 into 10 to the power minus 9, or you can say that minus 2 in approx minus 2 in that is 10 to the power 10 to the power minus 3 here, where we can say that with respect to this, with regard of that, the equilibrium lies mainly towards the undissociated water, and we can distinguish acidic, neutral, and as well as the basic aqueous solution by the relative values of H3O plus and OH minus concentration. So where we can say that, and we can write it down as well, that acidic is equals to, that is H3O plus is greater than OH minus. For base neutral, for neutral we have H3O plus is equals to OH minus, and for basic for we have H3O plus is less than OH minus. So that you have to note it down. For acidic, H3O plus is greater than OH minus, neutral में दोनों equal होते हैं, and as well as for the basic, this is less than OH minus here. Now we'll discuss another topic, that is your pH scale, that we have to discuss here. In terms of the pH scale, first we have to know about the pH scale, then we will discuss related to that only. For the pH scale, that the hydronium ion concentrated in molarity is more conveniently expressed on the logarithmic scale, that is known as the pH scale here. The pH of a solution is defined as a negative logarithm of the base of 10 or of an activity, like we denote by AH here, and of a hydrogen ion, and in a dilute solution that is less than 0.01 mole, and that activity of the hydrogen ion, that is H plus, is equals to the magnitude of the molarity represented by the H plus as well. And it should be noted that the activity has no units and is defined as AH plus is equals to H of plus per mole liter inverse. And from this equation, from this definition of pH, the following can be written as like a pH is equals to minus log A of H plus equals to minus log H of plus per mole liter inverse. Thus an acidic solution of the HCl is 10 to the power minus 2 mole and with half of pH 2. Similarly, a basic solution for of NaOH having OH, that is of 10 to the power minus 4 mole, and with regard of that H2 plus we have 10 to the power minus 10 mole with have a pH of 10. At 25 degree pure water has a concentration of the hydrogen ions H plus, that is of 10 to the power minus 7 m, and hence the pH of the pure water is given as like pH of we can say that the pH is equals to minus log A of H here, and where my equals to minus H plus per mole inverse, and with regard of that pH of that is minus log 10 to the power minus 7, that is equals to 7. For the acidic solution, possesses the concentrations of hydrogen ion, that is H plus, is greater than 10 to the power minus 7 mole, while the basic solution possesses the concentrations of the hydrogen ion, that is H plus, is less than 10 to the power minus 7, as I had mentioned here. Thus we can summarize that for the acidic solution, we can just write it on. For the acidic solution, solution has a pH of less than 7, and for the basic solution, pH is greater than 7, and for a neutral solution, we have a pH that is equals to 7 here. Now again consider the following equation like at 298 Kelvin, then we will be finding out that is Kw is equals to H2O, okay, and that is Kw equals to H3O plus, and then we have OH minus as well, is equals to 10 to the power minus 14. Taking negative logarithm on the both side of the equation, what we will finding out is minus log Kw equals to minus log H3O plus and OH minus. We're taking a log both sides, so what we'll get here, minus log H3O plus minus log OH minus. When finding out this, that minus log 10 to the power minus 14. Here that Kw equals to pH plus P of OH equals to 14. We note that although that the Kw may be changed over the temperature, the variations in the pH will be with the temperature are so small that we often ignore it, and pKw here is a very important quantity of the aqueous solution and controls that the relative concentration of hydrogen and hydroxyl ion as their product is a constant. It should noted that the pH scale is logarithmic. A change in the pH by just 1 unit also means that the change of H plus by a factor of 10. Similarly, when the hydrogen ion concentration, that is H plus, changes by a factor of 100, the value of the pH changes by the 2 unit. And now you can realize that why the change in pH with the temperature is often ignored. In reference to that, the measurement of the pH of a solution is very essential, as its value should be known when dealing with biological and the cosmetic application, and the pH of that solution can be found roughly with the help of the pH paper and has different color in solutions of different pH. Nowadays pH paper is available with 4 strips on it, that the different strips have the different color and at the same pH, and the pH is of the range is 1 to 14 only, that can be determined with an accuracy of approximately 0.5 using a pH paper. Where we have these pH papers have 4 strips that may have different color on the same paper of that same pH. And for the greater accuracy of the pH meters are used. That pH meter is a device that measures the pH dependent electrical potential of the test solution within the 0.001 precisions. And even though pH meters of the size of the writing pen are now available in the market, the pH of the some very common substance are given, will be discussed here in the table form. Now first of all we'll go on through with the questions, and that what we will solve here, and that is the question here. The question is that the concentration of hydrogen ion is a sample of soft drink is 3.8 into 10 to the power minus 3 m. What is the pH of it? So you have to find it out this, and with regard of that, here the solution will be that is of pH equals to minus log 3.8 10 to the power minus 3, what it is given here, that is equals to minus log 3.8 plus log 10 to the power minus 3. With regard of that, minus 0.58 plus minus 3.0, that is equals to minus 2.42, and that is equals to 2.42 here as well. With regard of 2.42 here, that therefore the pH of the soft drink is 2.42 and it can be inferred that is acidic here. Now we will go ahead with the question, that is another question, that is calculate the pH of 1.0 into 10 to the power minus 8 m solutions of HCl here. In regard of that, what we have to find it out in reference to this, that what we have to find it out is your like 2H2O, like let's solve it out. 2H2O liquid that gives H3O plus aqueous plus OH minus, that is in aqueous. For that, Kw equals to OH minus H3O plus here, and for that sake we have find it out value 10 to the power minus 4, where x equals to OH and that is equals to H3O plus from H2O. So the H3O concentration is generated, and from the ionization of the HCl dissolved in it, so the equation will be formed as HCl, that is in the form of the aqueous state, plus H2O liquid gives H3O plus aqueous plus Cl minus, that is also in the form of aqueous here. So here from the ionization of the H2O and these very dilute solution, both the sources of H3O plus must be considered as like H3O plus is equals to 10 to the power minus 8 plus x. So Kw equals to 10 to the power minus 8 plus x multiply x, that is equals to 10 to the power minus 14. In regard of that, or we can say that x square plus 10 to the power minus 8x minus 10 to the power minus 14 equals to 0. So here OH minus equals to x, which is equals to 9.5 into 10 to the power minus 8. So the POH is equals to 7.02 and pH is equals to 6.98 here. With regard of that, now we'll discuss some of the table regarding the pH of some common substances, and here is the table as you can see. And with regard of that, here the name of the fluid, we have to discuss about the pH, and there also in the name of the fluid and then pH we have to discuss here. So first, a fluid, we have saturated solution of NaOH. The pH of is, that is 15. The 0.1 mole of NaOH solution, here the pH is 13. Lime water, that is your 10.5. Then we have milk of magnesia, that is your 10. Then you have your egg white or sea water, that tells your 7.8. Then we have human blood, that is 7.4. And then we have your milk, that is 6.8. Next is your human saliva, that is 6.4. Then we have a black coffee, that is 5. And the tomato juice, that is your minus 4.2. Then soft drinks and vinegar, that is minus 3.0. Then we have your another one, that is your lemon juice, and lemon juice का होता है minus 2.2. And for the gastric juice, that is minus 1.2. And for the 1 mole of HCl solution, that is minus 0. And for the concentration treated HCl, that is your minus 1.0. So these were the pH of some common substances that you can just write it down, copy it out down. Now we'll move ahead with another one here, that is another heading, that is ionization constants of weak acid here. So here we'll discuss about the ionization constants of weak acid. With regard of that, you have to consider with a weak acid, that is of HX, as I had taken here, that is the partially ionized in the aqueous solution, and the equilibrium cannot be expressed. And for that, the equation we have is HX, that is in the form of aqueous state, plus H2O, that is in the form of the liquid state. It gives H3O plus an aqueous state, and X minus, that is in aqueous state as well. Initial concentration mole of that is C, we can say that this is 0 and 0, and let alpha be the extent of the ionization change of M, so that is C alpha and as well as C alpha. So with regard of the equilibrium concentration, so C is what we are taking is as in the form of the initial concentration of the undissolved acid and HX at a time, so where T equals to 0 and alpha equals to extent up to which HX is ionized ion into the ions. As well as using these notations, we can derive the equilibrium constant for the above discussed acid dissociation equilibrium, that is your Ka, that is equals to C square alpha square upon C 1 minus alpha, and that is equals to C alpha square upon 1 minus alpha. This Kw here, if Ka, that is the dissociation or the ionization constant, dissociation or ionization constant here of acid HX, and it can be represented alternatively in the terms of the molar concentration as follows, and that would be written as like Ka H plus X minus by Hx. This is the representation here. With regard of that, at a given temperature T, and the Ka is a measure of a strength of the acid of HX, that is, the larger the value of the Ka, the stronger is the acid, and that is your Ka is a dimensionless quantity, and it is understanding that the standard state of the concentration of all the species is 1 mole, and the value of the ionization constant of the some selected weak acids are as given. Like we'll discuss some of the ionization constants of some selected weak acid at a temperature 298 Kelvin here. These were the acid has been given, and this is the ionization constant Ka. We have to write it down. The first is your hydrofluoric acid, that is HF, a nitrous acid, that is HNO2, formic acid, that is HCOOH, and that is niacin, that is C5H4NCOOH, acetic acid CH3COOH, benzoic acid, that is C6H5COOH, and hypochlorous acid, that is HClO, and the hydrocyanic acid, that is SCN, and the phenol, that is C6H5OH. Now we'll write it down the ionization constant for all these. So here we will write it down some of the ionization constant here, and that we have, that is Ka. For the hydrofluoric acid HF, that the ionization constant we have is 3.5 into 10 to the power minus 4. Nitrous acid, that we have as your 4.5 into 10 to the power minus 4. Formic acid, for that we have 1.8 into 10 to the power minus 4, and for the niacin we have a 1.5 into 10 to the power minus 5. Then for the acetic acid we have 1.74 into 10 to the power minus 5. Then for the benzoic acid we have here is your 6.5 into 10 to the power minus 5. Then we have that is hypochlorous acid, and that for that we have 3.0 into 10 to the power minus 8. And then after that, for the next one we have your hydrocyanic acid, and that is your 4.9 into 10 to the power minus 10. And for phenol, that is 1.3 into 10 to the power minus 10 here. In regard of that, the pH of the scale for the hydrogen ion concentration has been useful, that besides a pKw, it has been extended to the other species and the quantities that we have. So we can say that with regard of that, that is pKw is equals to minus a log of Ka, and knowing the ionization constant, that is Ka of an acid, and its initial concentrations of C, that is, it is possible to calculate the equilibrium concentration of all the species, and also the degree of the ionization of the acid and the pH set of the solutions as well. With regard of that, a general stepwise approach can be adopted to evaluate the pH of the weak electrolyte as follows. So the step first we have here, the species present before the dissociation are identified as the Bronsted-Lowry's acids and bases. So with regard of that, the species present before dissociation are identified as Bronsted-Lowry acids and bases. With regard of that, the second is that you have to balance equations for all the possible reactions with the species as acting both as acid as the base are written. So you have to, second step is to balance equation. Balanced equation for all possible reactions. That is, with the species acting both as acid and as well as the base are written. Step third, the reaction with the higher Ka is identified as the primary reaction, while the other is a subsidiary reaction. So what you have to do in the step third, the reaction with the higher Ka is identified as primary reaction, and then while the other subsidiary reaction. The fourth step we have is that enlist a tabular form of the table and values of for each of the species in the primary section. So you have to make a table, tabular should be there, and with regard of that you have to first step में उसको भी आपको पहले देखना है कि initial concentration you have to find it out, that is C, and the change in concentration, change in concentration. So change in concentration on proceeding to equilibrium in terms of alpha and the degree of ionization, and the third in here is your equilibrium concentration. Then the step 5, what you have to do is you have to substitute equilibrium concentration into equilibrium constant equation for the principal reaction and solve alpha. And then after that, for the step 6, you have to calculate the concentration of species or in principal reaction. Where, and in the 7th one, you have to calculate the pH, that is minus log H3O plus. Okay, so this is the above mentioned method. That methodology has to be elucidated in the following questions that we are doing here, and that is the question here is that the ionization constant at HF is 3.2 into 10 to the power minus 4. Calculate the degree of dissociation of HF in its 0.02 mole and solution. Calculate the concentration of all species present, that is H3O plus, F minus and HF in a solution and its pH. And now we'll find it out with the solution here. For the following, we can say that the following proton transfers, that is the reactions are possible. Like first is your HF plus H2O, it gives H3O plus plus F minus, and where we have Ka equals to 3.2 into 10 to the power minus 4. For the second equation we have is H2O plus H2O, it gives H3O plus plus OH minus, where Ka equals to, yeah, Kw equals to, that we can say that that will be 1.0 into 10 to the power minus 14, and where Ka is more greater than Kw. So we can say that is the principal reaction, that is your HF plus H2O, that gives H3O plus here. With regard of that, H3O plus here plus F minus, and initial concentration for this is 0.02, then 0 and 0, and then 0 minus 0.02 alpha, then 0, and the substituting equation concentration in the equilibrium reaction for the principal reaction gives, that is you have is your Ka equals to 0.02 alpha square upon 0.02 minus 0.02 alpha as well, and for that we have 0.02 alpha square upon 1 minus alpha, and that is equals to 3.2 into 10 to the power minus 4. We obtain the following quadratic equation, that is alpha square equals to 1.6 into 10 to the power minus 2 alpha minus 1.6 into 10 to the power minus 2, that is equals to 0. The quadratic equation is in alpha can be solved, and the two values of the roots are, that is the alpha equals to your plus 0.12 and minus 0.12 as well. The negative root is not acceptable, and hence the alpha equals to plus 0.12 here. This means that the degree of the ionization, that is alpha, is 0.12 here. And then the equilibrium concentration of the other species OY we have is your HF, F minus or H3O plus are given, and with regard of that, H3O plus is equals to F minus, that is equals to C alpha, and that is 0.02 into 10, 0.12, and when further solve 2.4 into 10 to the power minus 3 m. And with regard of HF, that is equals to C 1 minus alpha, that is equals to, with regard of that, C 1 minus alpha here, that is equals to 0.02 A1 minus 0.12, and with regard of that 0.17.6 into 10 to the power minus 3 m. And for that sake we have find out pH, that is minus log H plus equals to minus log 2.4 into 10 to the power minus 3, and that will be the value of 2.62 here. Now we'll go ahead with another one, and that is the question, that is the pH of 0.1 m, that is a monobasic acid is your 4.50. Calculate the concentrations of the species H plus, A minus, and of course that's HA at equilibrium. Also determine the value of Ka, and that is your P of Ka of mono basic acid here. And with regard of that, we will be finding out the solution here, and that is your pH equals to minus log of H plus, and therefore we will find it out H plus, that is equals to 10 to the power minus pH, and that is 10 to the power minus 4.50, and we will be finding out the value of, that is 3.16 into 10 to the power minus 5. So we will be finding out the H plus here, and that is equals to A minus equals to 3.16 into 10 to the power minus 3, 10 to the power minus 5 here. Okay, so with regard of that here, thus Ka, we can find out the Ka equals to H plus A minus upon H of A, and with regard of that we can say that, and we will put value of HA, we will be finding out, that is 0.1 into 0.1 minus 3.16 into 10 to the power minus 10 to the power 5, that is equals to 0.1, and Ka equals to 3.16 into 10 to the power 5 2 upon 0.1, and that is equals to 1.0 into 10 to the power minus 5. And for pKw, minus log 10 to the power minus 8 is equals to 8 here. Okay, so this is also the 10 to the power 8 minus 8 here. With regard of that, alternately, if the percentage dissociation is the another useful method for measure the strength of a weak acid, and is given as the percent dissociation. So the percent dissociation we have is H of A dissociation upon H of A initial multiply by 100% here. Now we'll go ahead with another one, and that is the another question here. As you can see on the question, we have here is, as you can see here, that the calculate the pH of 0.08 mole and solutions of hypochlorous acid, that is HOCl. The ionization constant of acid is 2.5 into 10 to the power minus 5. Determine the percent dissociations of HOCl. Here for the solution, that first we have to know about the equation, that is plus H2O liquid gives H3O plus aqueous plus ClO minus. We will equilibrium constant for M, and we will find it out the K of A, that is equals to H3O plus ClO minus on HOCl that is equals to h square x square 0.08 minus x. With regard of that, because x is 2 less than 0, so therefore we can say that 0.08 minus x, that is equals to 0.08 here. And with regard of that, we can say that the x square slash that is 0.08 equals to 2.5 into 10 to the power minus 5, and where h square equals to 2.0 into 10 to the power minus 8. And here with reference to that, अगर मैं बात करती हूँ like where that is your minus 6 here, and in terms of the 6 we will go ahead that x equals to 1.41 into 10 to the power minus 3, and here for that h plus that is equals to 1.41 into 10 to the power minus 3 mole. Therefore the percentage dissociation, or we can say that the percentage dissociation is equals to HOCl dissociation upon HOCl, that is your after that undissociation multiplied by 100, and for that we will find it out 1.41 into 10 to the power minus 3 slash 0.08, that is equals to 1.76%. and for that sake pH equals to minus log 1.41 into 10 to the power minus 3, that is equals to 2.85. okay, so this is what we have to find it out, and how you have to find it out. Now moving ahead with another one, that is ionizations of weak bases. In terms of ionizations of weak bases here, in terms of this, the ionization of the base MOH can be represented by the equilibrium that we have equations like MOH is in the form of the aqueous state. It gives M plus aqueous and plus OH minus aqueous here. In a weak base, there is a partial ionization of MOH into the M plus or OH minus. This is the case is similar to that acid dissociation equilibrium, and the equilibrium constant for base ionization is called as base ionization constant, and that is represented by the Kp, and it can be expressed in the terms of the concentrations of molarity of the various species in the equilibrium by the following equation, that is Kb equals to M plus that is M plus and OH minus slash MOH, that as we had find it out many times. Alternately, if C is the initial concentration of the base and the alpha is the degree of the ionization of the bases, that the extent to which the base ionizes so when equilibrium is reached. So the equilibrium constant can be written as like in the form of the Kb equals to C alpha square, sorry, this is an alpha C alpha square here, so C alpha square upon C 1 minus alpha, and that is equals to C alpha square upon that is 1 minus alpha here. The value of the ionization constant of some selected weak bases, that is of Kb, that are given here in the table, that we will discuss the values of the ionization constant of some weak bases at 298 Kelvin. They are the bases given, and we have to Kb write it down. The bases are dimethylamine, that is CH3 whole twice NH, and then a triethylamine, that is C2H5 3, and ammonia, that is NH3 or NH4OH, quinine, that is a plant a product, and that is pyridine, that is C5H5N, and aniline, that is C6H5NH2, and then urea, that is CONH2 ka whole twice. With regard of that, here we have to find out with this, and for the dimethylene, the Kb we have is your 5.4 into 10 to the power minus 4. For the triethylene we have is your 6.45 into 10 to the power minus 5. For ammonia we have 1.77 into 10 to the power minus 5. Then for quinine we have 1.10, that is 10 to the power minus 6. And then for the next pyridine, that is 1.77 into 10 to the power minus 9, that we have here. And then after that we have The next one, that is for the aniline, and that is your 4.27 into 10 to the power minus 10, and for the urea we have 1.3 into 10 to the power minus 14. With regard of that, many organic compounds like amines and weak bases amines are derivatives of the ammonia, so in which one or more hydrogen atoms are replaced by the another group. For example, like methylamine, that we had talking about, and for that sake, methylamine, codenine, quinine, and of course that is your nicotine, all behave are very weak bases due to the very small kb. Ammonia produces OH minus in the aqueous solution, and with regard of that aqueous solution, we have an equation here that you can see that NH3 in the form of aqueous state plus H2O in the form of liquid state, it gives NH4 plus aqueous state plus OH minus aqueous state. So the pH scale for hydrogen ion concentration has been extended to get here. With regard of that, pKb equals to minus log of kb here. Now we'll discuss the one of the questions regarding this, and that we have here is the question that is the pH of 0.004 H hydrazine solutions is 9.7, and that is calculates its ionization constant kb and pkb here. And with regard of that, we can say the solution for the equation, we will just write it down, that is NH2 here plus H2O, that gives NH2 NH3 plus OH minus here. With regard of that, from the pH that we can calculate the hydrogen ion concentration, and knowing the hydrogen ion concentration and the ionic product of the water, we can calculate the concentration of the hydroxyl ion. Thus we can have we can write it down like HO plus equals to anti-log of minus pH. Then we'll be finding out that is you have your anti-log minus 9.7, we have 1.67 into 10 to the power minus 10. Then we have OH minus, that is equals to K W upon H plus, that is equals to 1 into 10 to the power minus 14 upon 1.67 into 10 to the power minus 10. Then we have 5.98 into 10 to the power minus 5. The concentration of the corresponding hydrazinium ion is always the same as that of the hydroxyl ion. The concentration of both these ions is very small, so that the concentration of the undissociated base can be taken equals to the 0.004 here here. With regard of that, we can say here in terms of this, we can say here with regard of this that thus the kW, we can find it out, kW equals to, sorry, kb equals to, that is your NH3 NH2 NH3 plus OH minus upon NH2 NH2, that will give 5.98 into 10 to the power minus 5 the whole twice upon 0.004, which will give 8.96 into 10 to the power minus 7 here, where pkb log is minus log kb, so we'll just find it out like that also, that pkb equals to minus log kb, and that is equals to minus log 8.96 We'll just finding out for that is log that is into 10 to the power 7, and then we find it out 6.04. That will be the right answer. Now we'll find it out for the next question here, that will be having as your to calculate the pH of the solution from mixing of 0.214 that is 0.2 mole here, and NH4Cl, and zero point 0.1 mole of NH3. That the pOH of the ammonia solution is 4.75. So the equation will forming is NH3 plus H2O, and that gives your NH4 plus OH minus. And with regard of that the ionization constant for the NH3 is your that we can say that Kb equals to anti log minus p kb, and for that we will be finding out the kb here, and that kb equals to 10 to the power minus 4.75, that is equals to 1.77 into 10 to the power of minus 5 your mole. And with regard of that, with the another equation, that is the NH3H2O, it gives NH4 here plus OH minus. The initial concentration is 0.10 after, then after that change to the reaction reach equilibrium, that minus x plus x at an equilibrium m, then it is 0.10 minus x, 0.20 plus x, and plus x. With regard of that we have to find it out the value, and for that we will be just going ahead like kb equals to, that is NH4 plus OH minus, and that will be NH3 as well. And in regard of that we will solve the value, that is your 0.20 plus x, and that is x here as well, and that is divided by 0.1 minus x, and that will give 1.77 into 10 to the power minus 5. For kb is as small, we can neglect the x in the comparison of 0.1 mole and 0.2 mole. Thus we can say that the OH minus is equals to x, and that is equals to 0.88 into 10 to the power minus 5. So therefore we can say that the H plus here, and that will be equals to 1.12 into 10 to the power minus 9, and for pH that is equals to minus log H plus, and that is equals to 8.95 here. And in regard of that we will go ahead with another topic, and that what we have to discuss here, that is the reactions relations between the Ka and Kb here. We will end up this class as of now in chemistry unit 1 we had discussed, that is some basic concepts of chemistry, that is the importance of chemistry, nature of matter, properties of matter and their measurements, uncertainty in the measurement, laws of chemical combination, Dalton's atomic theory, atomic and molecular masses, mole concepts and molar masses, percentage composition, stoichiometry and stoichiometric calculation. And then we discuss about the structure of atom, and that is some atomic particles, atomic models, development leading to the Bohr's model of atom, Bohr's model of hydrogen atom towards the quantum mechanical model of the atom, and quantum mechanical model of atom as well. Then in unit 3rd we had discussed about the classification of element and the periodicity in the properties, that is why do we need to classify element, genesis of the periodic classification, modern periodic law and the present form of the periodic table, and nomenclature of the elements with the atomic number that is greater than 100, electronic configuration of element of the periodic table, electronic configuration and the types of element, that is S block, P block, D block and F block here. And then we had done the periodic trends in the properties of element, and after that we had started with unit 4. And in unit 4 if I'm talking about that we had done in detail as well, and unit 5, unit 6, unit 7 as well. So with regard of that if I'm talking about so here this is unit 4, that is a chemical bonding and a molecular structure, where we had discussed about the Pascal's approach to the chemical bonding, ionic and electrovalent bond parameter, the valential electron pair repulsion theory, that is whisper theory, valence bond theory, hybridization, molecular orbital theory, bonding in some homonuclear diatomic molecules, hydrogen bonding. And then unit 5, states of matter, that we had discussed, where intermolecular forces, thermal energy, intermolecular forces versus thermal interaction, the gases state, the gases law, ideal gas equation, kinetic molecular theory of the gases, behavior of real gases, deviation from the ideal gas behavior, liquefaction of gases and liquid state. Then we had done your unit 6, that is thermodynamics, thermodynamic state, application, measurements of delta U and delta H calorimetry, enthalpy change, delta R of H of a reaction, enthalpy of all the different types of reaction, spontaneity, Gibbs energy, change and equilibrium, that we had discussed. In Unit 7, equilibrium, we have to discuss about equilibrium in the physical process, equilibrium in the chemical process, dynamic equilibrium, law of chemical equilibrium and the equilibrium constant, homogeneous equilibrium, heterogeneous equilibrium, application of the equilibrium constant, relationship between the equilibrium constant K, reaction coefficient Q and the Gibbs energy G, and the factors affecting the equilibrium, ionic equilibrium and the solution, acid, bases and salt, ionization of acids and bases, buffer solution and solubility of the equilibrium and the Spagley soluble salt. That's what we have to discuss in the further classes. सो फर्स्ट ऑफ ऑल अगर आप हमारे चैनल फर्स्ट टाइम देख रहे हो या अभी तक आपने हमारे चैनल को सब्सक्राइब नहीं किया है, इट्स अ ह्यूज रिक्वेस्ट कि आप हमारे चैनल को सब्सक्राइब करो सो दैट हम जो भी वीडियोस डालें वो आपके पास सबसे पहले पहुँचे. एंड सेकेंडली, अगर आपको हमारा वीडियो अच्छा लगे तो प्लीज़ हमारे वीडियो को लाइक, शेयर और सब्सक्राइब करो. विल मूव अहेड विद सो ऑन एंड होपफुली इन द नेक्स्ट coming class we'll end up with chemistry. Thank you. Hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on the comment box. Thank you.